There were a couple of areas that have been discussed a little bit, which I wanted to elaborate on because I think it's significant. One of them relates to intact aborts, the question of a crew escape system, and whether that should be automated, whether the crew should have control, and what is required if you actually have the crew take control. I think Chris Kraft gave an interesting perspective with the idea that because of the difficulties, or given the requirements, really the impossibility of incorporating a capsule escape system for the shuttle, the project basically took the point of view that the shuttle itself was the escape pod, which means that you have to recover the shuttle intact regardless of any engine failures. Now that, of course, requires 100% reliability of the solid rocket boosters, which we never did achieve with Challenger. Although, of course, had we operated it within its spec limits, it might be another story. But in any case, I want to go through some of the details of a return to launch site abort, and then I'll describe an incident which occurred on our last flight to give you an idea of what's involved in the actual operation of abort modes. So the idea is, you have the two solid rocket boosters which have to light, okay, and they're going to perform no matter what. If one of those boosters doesn't light and the other does, it's a bad day. What can you say? And obviously, if one of them fails during flight, it's a bad day. And which was more of a design problem, if they don't tail off at just the identical rate, so that you get asymmetric thrust greater than a certain capability of the shuttle to control, you've had a bad day. And because of the requirement to have symmetric thrust, I don't think this was discussed before. When the solid rocket boosters are poured, they mix a batch of propellant, sort of like you mix bread dough, and then they pour the propellant into both the left and the right booster segments at the same time. So each booster segment has the identical batch of propellant in it. It may not be the same from the bottom to the top, but it's the same from the left to the right, and that's critical to make sure that. And then they always reserve a certain proportion of the propellant, and they do tests on that to make sure that it's there's no process control problems. Okay, so you still need the three main engines to have enough thrust. The boosters each give you about 2.5 million pounds thrust, so that's about 5 million pounds to get off the ground. These give you about 500,000 pound thrust at vacuum, 400 and some odd thousand pounds thrust, so still over 1 million pounds thrust. And of course, the problem you have during first stage is you've got big gravity losses. If the shuttle on the pad weighs about 5.5 million pounds with all the propellant, so if you don't fire your main engines, you're barely going to lift off the ground. Actually, I guess it's a little bit less than 5 million pounds. But in any case, without the three main engines firing, you don't have enough thrust to get into orbit. Now, remember we talked about for deorbit burn, you can have. Normally we fire both OMS engines. If one of the OMS engines is out, you can fire one engine for twice as long, or if they're both out, you can fire the 4 RCS thrusters for twice as long again. Because you're in orbit, you're weightless, you don't have gravity losses, so firing half as many engines for twice as long is completely equivalent. When you're taking off against gravity, that's not true. I mean, if you only have 5 million pounds of thrust for a 5 million pound payload, you're just going to sit on the pad and burn all your fuel. So, okay, so you need your three engines. So if you lose, and in fact, another interesting point. You know, the attachment between the external tank and the shuttle, that is stressed to assume that you have at least one engine burning. They tell me that if the shuttle took off with just the solid boosters and you didn't have any thrust, you know, sort of keeping the shuttle up with the external tank, that the structural attachment points would fail. So anyway, you need your engines. Okay, so what happens if you lose an engine early on? If you're far enough into the launch, you're over the main gravity loss segment, usually starting at about 3.5 to 4 minutes into launch. If you lose one engine, you can make it over the ocean, and that's called a transatlantic abort. And when you do that, you know, you're flying upside down. You'll do a roll maneuver, drop your external tank, and come in and land. And it's you know, you're basically going in the same direction, which is nice when you're flying a rocket. These things are hard to turn around. But if you're going to do a return to launch site abort, that's exactly what you have to do. So this is a procedure that has been analyzed to death in many, many computer simulations. The basic procedure is you take off, right? You lose an engine. Now it doesn't matter when you lose an engine in the first 2.5 minutes. You don't do anything while the solid rocket boosters are firing. They basically have open loop guidance. You know, there's a certain trajectory programmed in, and you can't readjust that trajectory with a closed loop guidance solution to accommodate for any sort of a malfunction. So you don't even declare an RTLS abort, and that by the way is done by the crew punching a button, which is essentially it's a protected button. And you punch that, and you can also do it via a computer input if something goes wrong with the button. So you declare an RTLS abort after SRB separation. Immediately what happens is your trajectory increases because you want to gain altitude, and you'll see why in a minute. Because what happens now, you've got a pretty hefty downrange velocity already, and you've got to turn around and come back. You've also got to worry about the disposal of your external tank. You don't want your external tank, you know, if you turn around and you come back, you're still burning your engines, you're still riding your tank. You don't want the tank coming down on Melbourne or Disney World or anything like that. So the basic procedure is as follows. You're going out, you loft your trajectory a bit. Once you get far enough out, now what you do is you do a powered pitch around. Very sporty maneuver, okay? The external tank is here. All right, now you're flying backwards into your plume. Everybody has speculated on what that would actually look like, all right? So now you're flying backwards, decelerating, okay? And as you decelerate, of course, gravity is starting to push you down, so you've got to increase your pitch velocity until finally you have no more horizontal velocity. You're basically just sitting statically on top of your exhaust, all right? And now you gradually pitch forward and you start to fly back. And again, you've got to plan your trajectory so that when you drop the tank, it's going to come down in the ocean. And then, if all that goes well, now you enter the heading alignment circle, and of course you're a heavyweight vehicle because whatever payload you had. But you also, in the process of the RTLS, you dump your OMS tanks and your RCS propellant so that you want to make yourself as light as possible. Plus, in case you have any problem with landing, you don't want your hypergolic propellant tanks to rupture. So if all that goes well, now you enter the heading alignment circle and you've got hopefully a nominal landing. As I say, this has been analyzed in high fidelity dynamic simulations. the crew practices it over and over again. Everybody knows the procedures. Nobody wants to be the first crew to try this out. Before STS-1, you remember we talked about how there were lots of problems with the tiles falling off. And so I remember one of the people very high up in NASA, don't remember if it was the administrator or one of the deputies, or suggested that maybe the safest thing to do would be to do a planned RTLS, because an RTLS, of course, you don't get up to those high velocities, and so you don't have any thermal problems. And so if a whole bunch of tiles had fallen off on the launch pad, you could safely do an RTLS. Well, obviously they did not appreciate the difficulties of doing an RTLS, and that suggestion was not taken up. We basically decided we were not going to fly until we had confidence that the tiles were going to stay on. Okay, cut forward to February of 1996, which was my 5th and final shuttle flight. So I was the second flight engineer, so I was sitting right behind the pilot who's responsible for the main engine performance. Now, I should tell you, we've had, in the course of the 114 shuttle flights, we've had 4 pad shutdowns, pad aborts. And I think we've talked about that briefly. The main engines turn on 6 seconds before the solids. That, just reviewing, that does 2 things. It gives you time, it gives the engines time to come up to full thrust, and then you can perform checks on them to make sure that they're operating properly before you commit yourself to flight. And, of course, it gives time for because of the asymmetric thrust, it gives time for what we call the twang, that the whole shuttle stack goes forward and then back, and then when you get to the vertical, you light the boosters. In fact, when they had the first test firing on the pad before STS-1, one of the reasons that they wanted to do that, in addition to just confirming that everything was working right, they really wanted precise timing on the twang. People had calculated it, but that's not something you want to get wrong, so they wanted an experimental verification. So of the 4 pad shutdowns, 2 of them were caused by instrumentation, and 2 of them were real engine problems. I remember the first one was the last flight before what would have been my first flight back in 1984. The main engine cutoff is called MECO, okay, so 8.5 minutes into the flight. And after they had a pad abort, the flight engineer called to mission control, we have MECO, somehow I thought we'd be a little bit higher. And of course, when that happens, now you've got to pull all the engines out, take them back to the shop, bring in new engines, and it's about a 2 or 3 week stand down, and the crew has to go back to Houston, and of course all of your friends and family are there, and they have to go home, and it's no fun, but nobody complains if it's safe. So okay, so we're sitting on the pad, we're counting down, and everything was on schedule. It was in fact the first of my 5 flights that it had 0 problems, 0 delays. We were going on the day that was predicted, on the time. Countdown to 6 seconds. You can feel the engines, everything starts to rumble, the engines start up. There's a kind of we call it a steam gauge. It's a vertical bar which shows the engine power. Center and right engines come up to 100%. The left engine comes up to 40%. Pilot calls out left engine at 40%. In times like this, your mind is working pretty fast. So, I remember thinking to myself, oh, damn, we're going to have a pad shutdown. We got to go back to Houston, back to the simulators, all of the, stupid things to be thinking about at that time, but that's sort of the way it works. And all of a sudden, kaboom, I feel this big kick in my back. The solids have lit. What in the hell is going on? We're supposed to have a pad abort. Now we're going with with an engine, and actually when you're going through maximum dynamic pressure, max Q, the engine's throttle down to about 65%. And there is a malfunction if one of your engines gets stuck, that's called getting stuck in the bucket, in the thrust bucket. If it doesn't come back to full power, your RTLS abort. Well, we were taking off with one engine at 40%. So, I sort of dawned on me that, we were going to be the first crew to do an RTLS. So at that point, I start going for my checklists, and the pilot calls to the ground, we have ignition, left engine at 40%. And so for about the first 15 seconds or so, I just had barely time to get out the RTLS checklist and start getting ready to read the procedures. And then it turns out that the ground has more insight than the crew does, and it turns out that there's several sensors, one of which feeds that gauge, but in fact that sensor had gone bad, and in fact the left engine was performing nominally, and the ground was able to confirm that from both by the other sensors and by looking at the acceleration, and so everything was okay. I put away the checklist and enjoyed the ride. But it's first of all, it was kind of a scary situation, but it also shows the difficulty. Now, suppose, we as the crew had been responsible for declaring an abort. If you're going to build in a system where this is the crew's responsibility, then you better design your instrumentation so that the crew has all the instrumentation required to make that decision correctly. And similarly, if this were going to be an automatic abort, how you've got to have failure detection, identification, reconfiguration, so that the last thing you want, is to go into an abort situation when you don't have to, because there's no way that an abort is going to be anywhere near as safe as a nominal mission. So I think it was obviously it's just a good story now, but I think it does have something to inform about how you're going to have to design abort systems, and as both Aaron Cohn and Chris Kraft said, that although the astronauts always felt comfortable with their abort system, but I'm not sure that all the people in mission control were quite so comfortable knowing the things that might go wrong with it. And in fact, as he said, they always breathed a sigh of relief when, after first stage, when the abort rocket would detach and fire itself away. Yeah.
When one of the engines is not working or not working properly, I guess the other two engines are trying to do the work of first engine or something.
Well, they certainly will throttle up to 109% if they need to, but they can't make up for the first engine when you're in the first stage and you have lots of gravity losses. In fact, up to about when you get, like I said, to about 3.5, 4 minutes, then you have enough altitude and downrange velocity to make it across. And then at some point you get to the situation where you've basically gained your altitude, and although you're not at orbital velocity yet, so you still have some gravity losses. The gravity losses are small enough that if you have a loss of an engine, you can still make it to a lower orbit. That's called abort to orbit, and it's ATO, and you'll hear the call press to ATO, single engine, press to ATO means that you can now make it to a lower orbit, which is the safest thing to do with two engines. And then a little bit later on, you'll hear like single engine TAL, which means if you lose two engines, with only one engine you can make it across the Atlantic. And then later on you'll hear single engine ATO, and then finally single engine. Then you'll also hear the press to MECO, which means at this point if you lose an engine, you can make it to your nominal orbit. And usually about the last call is single engine press to MECO, which means even if you lose two engines, you can still make it to MECO.
What happens then if there's an instrumentation problem, which I mean, in the cockpit you're seeing some values that are not right.
The crew,
how does that?
the crew will never on their own. The crew will never declare an abort on their own, because it's just realized that the ground has so much more information. The only exception is if you lose comm. You know, if we had lost comm, you know, and we saw our engine at 40%, and we didn't. I mean, there were a few other displays which the pilot was starting to call up, and it could be that he would have figured it out, perhaps not. But that's the only circumstance under which the crew would make that call. Yeah.
There was one abort ATO at some stage. What happened there? Did they manage to make it?
I was trying to remember if did I talk about that in class? Well, all right. I'll run through that because it was again a very interesting story. You know, you have one of the things that you're afraid about is that if things go bad in a hurry in an engine, that an engine can actually blow up. And you know, it's one thing if an engine gets shut down. Now you're just flying on two engines. But if an engine blows up and takes out your whole rear section, you've had a bad day. Okay, so the instrumentation is biased towards an early shutdown. If you sense that something's going wrong, shut it down. You know, we've got intact aborts. You know, better to err on the side of safety, even if that might potentially put you into an abort situation. And I'm trying to exactly reconstruct it. The thing is that if you lose one engine, all right, so now you are abort ATO. Now if you lose a second engine, you might be in a situation where certainly you can't make it to orbit, and because you've changed your trajectory, you might not be able to make it to a good transatlantic landing site. So at that point, if you have lost one engine, there is a switch on the center console where you can override the engine shutdown command. So what you're now saying is, we're in an unsurvivable situation if we only have one engine, and therefore we'll take the extra chance of getting an instrumentation-caused engine shutdown. We're not going to take that chance, so we are going to disable the ability of instrumentation to shut down the engine, and we'll just take our chances. The ground will continue the calculation, and as soon as you get to the point where you have the capability of doing a single engine TAL or a single engine abort to orbit, you re-enable the instrumentation. So what happened, the shuttle launched, it must have been about 4 or 5 minutes into launch, because they lost an engine. It shut down automatically. They're now abort to orbit, lower orbit, but they were abort to orbit. Take the switch, put it to inhibit. Now, the main propulsion flight controller was very good. She realized right away that it was an instrumentation problem, you know, because sometimes if you can see certain trends, or you see things change in a way that tells you that this is not the way a real engine behaves, that this is more typical of instrumentation. So she suspected she had an instrumentation problem. All right, now they get a little further along in the launch, where they could have potentially done they were too far to land in the normal TAL sites, which were in the daytime on the west coast of Africa, but they could have made a nighttime landing at some emergency airport in the Congo, I think it was, if they had lost another engine. But by the flight rules, they take the switch back to enable, so that now, because you can safely, quote, safely lose a second engine, you want to protect yourself against an explosive situation. So now they're enabled. All right, now the flight controller sees that the instrumentation on one of the other two engines is starting to go bad the way the first one was. And she realized that, in about 15 seconds, that engine was going to shut down. So she immediately called the flight director and said, flight, take the switch back to inhibit. And luckily, this is where the discipline becomes very important. The flight didn't get into a long, involved discussion about why do you want to do that, what's going on. Just said, Capcom, engine switch to inhibit. They took it, and sure enough, the instrumentation went bad, but the engine was okay. They got to orbit. Then they used some of their OMS propellant to raise their orbit a little bit, and that was a Space Lab mission, and they had a good mission. But the flight controller actually won a big award for that because she really saved the day. So that's the closest we ever came to a real intact abort. Yeah.
Two questions. The first one is on going back to the return to launch site. Does all of the main engine propellant get used up before the tank is dropped, or do you not burn some of the propellant?
I don't know the answer to that. I don't.
And the other one is on the pad with your flight. Wouldn't the sequencing computer shut down the other engines if it detected that one of them had failed?
Well,
and so it must have used the good sensor.
Yeah, that's right. And luckily, our little gauge was just fed by one. I mean, and in retrospect, you can say, well, probably that's not a good way to design it, but that's the way it was designed. You're right. If the engine controller senses with a majority or however they program, I don't know the details of the guts of the software there, but if it's convinced that one of the engines is not working right, it shuts down all three engines, which is, that's what happened on 4 occasions. Okay, yeah.
When you talked about the force pitch over and the return to launch site, is that just the gimbling of the main engines that gives you that?
Yeah. Yeah, because you're off the solids at that point. And that's the thing. I mean, with the solids, there's such an enormous thrust, and the aerodynamic loads are huge. You don't want to deviate from your planned trajectory because one of the things that they do is they program in load relief for the aerodynamic surfaces. They take the day of wind's launch, and if you have wind shears or other atmospheric high jet streams that you're going to fly through, they actually program the elevons and the body flap to move in such a way as to relieve the aerodynamic loading on the wings, and that's pre-programmed in. It's not a closed loop. It's totally open loop. So you don't want to change the trajectory once you've put all that load relief in.
How long does that pitch over take?
It's pretty quick. It's about 10 seconds if I remember from the simulator. It's a sporty maneuver, I'll tell you. I mean,
no RCS that goes into that? No RCS?
Oh, the RCS is trivial compared to what you're getting out of, You've got 500,000 pounds coming out of each engine. The RCS is the primary RCS is 750 pounds. So but they, like I say, they do then open up the RCS as you're flying back, and what they do is they open up all the engines so that you have symmetrical thrust, so that it doesn't, you're firing out of both sides. So that the idea is just to deplete the tanks as much as possible. Okay. The second technical area that I had been hoping that Al Louviere would get into and didn't have a chance to was the payload bay doors, which are a fascinating mechanism. And it's also going to be a segue into EVA because originally, it was a strange situation. It's kind of hard to relate back to that now when you look at how many successful EVAs have been done, and the Hubble repair and the building of space station and all the other things. But management at Johnson Space Center was not particularly friendly to EVA back in the 70s. Now, I asked Chris Kraft about that, and at first he denied it. He said, well, I always liked EVA. he said, well, maybe it was the management of the astronaut office that didn't like EVA. He did admit that Bob Gilruth, who was the director of Johnson Space Center at the time, this is when Chris Kraft was head of flight operations, Bob Gilruth definitely did not like EVA. He was afraid of it. He didn't think it was safe. Despite the fact that, back in 1973, EVA had saved the entire Skylab project. I don't know, hopefully most of you know that story. I know it's ancient history, but and clearly we had done a lot of safe EVAs on the surface of the moon, but basically EVA was looked at, it was expensive, it was potentially hazardous. Given the things that the shuttle was supposed to do in the original planning, mainly launch satellites, launch pieces of the space station, that went away, launched Defense Department satellites, commercial satellites. EVA was not really part of the big picture in planning, and although they did design an airlock for the shuttle, there were real questions of how much preparation do we have to do for EVA? Do we really even need it? Maybe we could save some weight by not having spacesuits aboard. Okay, so, I know what I was going to do. I was going to set up the remote here. Let me do that. Hold on just a second. Uh-oh. Okay, so that's where we finally ended up. That's the Hubble telescope. This is the payload bay, side of the payload bay. So, obviously EVA became a very successful activity, but these are the payload bay doors. This is in the orbiter processing facility. One of the things, I have a picture of closing the door, but the mechanism of these doors is extraordinary. There are two motors, one at the front and one at the back of each. Each of the motors has two drive units, and they work through a differential, so that if one of the motors fails, the other one can still drive, although at half the speed, just similar to the way a car works. There's a long torsion rod which runs the length of the shuttle, and then that torsion rod is attached to these bars over here. I'm sorry the picture was scanned in and it's not terribly sharp, but as the torsion bar twists, then these rods lift up the payload bay door and bring it to a close. And the mechanism, this is the best picture I could find, and you notice there's a strong back because as was mentioned, the doors can't support their own weight in 1G. But the system of latches here, you have to remember that the payload bay can expand and contract by several inches due to thermal environment. And so you have to design a latch system that can accommodate this thermal behavior. It was an incredible mechanical challenge, and the complexity of this system. I'm always amazed when I look at how the thing works. I have a schematic of them later, which you can look at. But basically, you close the doors, and then the first thing you do is you want to close the latches on either end, and then there's also centerline latches. And I think Al Louviere did discuss the fact that these payload bay doors are part of the structural element of the shuttle during reentry. You cannot reenter if the doors are not just closed but latched. You need them latched for structural strength. So there's a series of bollards here, little protrusions, which these latches grab on, and they've designed the rigging of the rods such that the latches that are close to the hinge line actually close before the latches that are further away. So it's a sequential closing of the latches, all with a single mechanism, so that you basically you pull the part of the door that's closest to the torque rod, you latch that down first, and then it's kind of a zipper effect where then you pull it down so that even if the door is a little bit warped thermally, you'll get the door to close properly. You wouldn't want to close this latch first and then have the door in a situation, where it was buckled out. Whereas here, and then of course the centerline latch, because of the thermal expansion, you can have the doors coming together like that or like that, and you've got to have centerline latches that can accommodate for that. So it's really quite an incredible design. And Al Louviere had said that he was going to talk about it, but he didn't have time to. Well, anyway, there's plenty of redundancy in here because there's these double motors, but because this is so critical, people started to look at, suppose you got some debris stuck in the mechanism. Doesn't matter how many motors you are, you can't get it closed. Suppose the motors jam on one side. Now the other motor isn't going to be able to drive it. So various things were done to allow for EVA intervention. And in the early shuttle flights, this was the only thing that the crew trained for with EVA. It was just payload bay door contingencies. Okay, so for instance, the PDU, the drive unit, this is the payload bay door drive unit, or PLBDU. That's what we call a nested acronym. Okay, that's part of the game there. So you have to go out and you peel away the liners of the payload bay, and inside here there's a little mechanism where you can insert a special tool and twist it, and that actually disconnects that motor drive unit from the torque, so that it can turn freely. And I hope when you look at these things, you'll get some sense of the complexity of these mechanisms. And so what we do, for training, of course, they build mock-ups of this in the water, and we also look at the real shuttle down in Florida to actually see these units. And for the people who are on the EVA crew, you spend a lot of time crawling around the payload bay, getting intimately familiar with a lot of the actual mechanisms, just in case you actually have to go out and do something with it. Then suppose the problem is not with the drive unit, but that one of these latches gets jammed up. So this is actually a tube cutter. It's a little hard to see, but I don't know if you're familiar with the things. They're on a ratchet, and as it gradually cuts, you push the blade in bit by bit, and then eventually you cut away. And this gives you an idea of some of the other. They just gave us a lot of tools, a pin extractor, a crowbar, vice grips, you name it.
How much that crowbar cost?
Well, the crowbar probably cost about $10 at Sears, and then they had to put on all of the Velcro and the tethers to go in the tool thing, and that probably cost a few $100s, and then they had to make a drawing of it, and you know how it goes. And so EVA is very expensive because everything has to be custom made. I mean, that's one of the things that, because of the constraints of the suits and the gloves, you can't, in most cases, just use regular tools. And as I say, everything is tethered, and I'll show you pictures later. We have a little mini workstation. They built little receptacles on the side of the suit because it's a hard upper torso, which can take a certain amount of load, and so you plug basically a tool caddy into your suit, and then you hang all of these tools on the tool caddy, and you'll see some pictures later of how that works. So then if the motors don't work and you've now freed the doors so that the door can move, but you have no motor to drive it, so now we have a mechanical winch and a rope on it, and so I'm not making this up. So you actually run the rope up. These are the little bollards that the latches catch onto. You run the rope up over that, and then you have to crawl out on the payload bay door, which would be a lot of fun, but and attach it here, and then you actually wind it closed. And we do this in the water. I mean, they have, this is all fully mocked up, and yeah.
What do you do if you have trouble opening the doors just after launch?
Well, if you can't open the doors, then you come home. Yeah. You wouldn't want to. I mean, if there's something seriously wrong with the doors, you better come home. Because, you know, yeah, we can do this to get them closed, but you don't want to purposely put yourself in that situation if you know you have a problem beforehand. Yeah.
How many people would it take to go from closed to payload doors? It depends on the problem.
We think it could be done with one person. Normally, we only go out with two, but in the orbital flight test, the first 4 flights only had 2 crew members. One of them was EVA trained. And then what happens if you get the doors closed but the latches don't latch? So they gave us, they actually made latches that we could put on by hand. So these are the latches for the side, and this is the schematic that sort of shows, you know, the latches go on the rollers in that order, 1, 2, 3, and 4. And again, you know, the way they designed this so that they actually close in sequence, but you only have one drive unit is really, I mean, it's just a beautiful mechanical system. But if they don't close, then you take this, and I won't go into the details, but you have to spring it around at least 2 of those, and that will give you the structural strength to come home. And then if the center line latches don't close, again, you can look at the mechanism here, and they have yet a different tool. Now, this is actually shown on its side, but this is actually on the top. And this is a bitch in the water because, you know, yeah, your suit is weightless, but the tool is not. And so you're holding this tool, and so when you're holding the tool, you want to sink to the bottom, and so you're trying to hold on with one hand, and you have a tether, so you try to tie yourself to the top there so that you're kind of hanging on the tether. But then, depending on how your way out is, you know, if you move this big tool back and forth, your body is sort of rocking back and forth, and you're working above your head. So I mean, everybody has to do it. I mean, if you're going to be an EVA crew member and you can't do this job, you're disqualified. But nobody likes it. It's a real pain. Anyway, so that is basically how EVA got sold to the shuttle system. I'll show you a few pictures of general EVA activities to give you an idea of how the system works. And then I want to go into the question of the interaction between EVA and the pressurization and the environmental control system of the rest of the shuttle. Because again, this is a systems engineering problem, and you can't, in most cases, do one thing without it having an impact on something else. So, you know, I talked about doing all those training. Now we're stepping 10 years into the future, so that's training for the Hubble telescope. And actually, the telescope is so tall that we couldn't get the whole thing in. The pool wasn't deep enough, so we had to actually cut it in half, and we would work on one half and then work on the other half. You know, here's an example. This is me installing the wide field planetary camera. Now, the training, people normally see the water tank. You're not weightless. You all understand that. If you go upside down, the blood rushes to your head. If you're holding on to tools, the tools will fall down. And more to the point, well, and of course, you don't have these guys when you're out in space, but angels, if you saw them out there on this point, I don't know. Anyway, if you're moving around large objects, they have resistance from the water. So you need to get a sense of how easy it is to push things around so you don't get things moving too fast. So we also train on air-bearing floors. This is a mass model of the WIFPIC, same mass, moments of inertia. so that, and I'm up here on a weight relief system, and you can really get a sense of what it feels like, and so you're trying to build a kind of a muscle memory so that when you get in space, you're not trying to push things as hard as you push them in the water, and you also remember that if you want to stop something, you also have to be able to exert a force on it, whereas in the water, all you have to do is to stop pushing. So now we go into space, and we're ready for the EVA, and I'll sort of take you through what's involved to give you a sense of the complexity of this system. So first of all, our tools. That's what I look like before all the cosmic rays made my hair fall out. It's just one of the hazards of spaceflight. So, okay, so here you see the kind of tool caddies. This is for a ratchet wrench, and we had about 250 different tools, about 100 planned to use, and the rest were for contingencies. And we had to take them all out, so we had them on, we call this our fish stringer. You sort of like, Portuguese fishermen, fisher wives hang all the fish on the string and then hang them out. So, and then we take this out on the fish stringer. So this is the airlock at launch, and it's totally packed. And in fact, we had 4 spacesuits rather than the normal 2. So there wasn't a whole lot of room. And first thing you go in is you go and you start checking the various systems, and then you have to unpack everything and move it into the flight deck. So that's story. We went out together, and this is the hard upper torso. This is looking down into the inside of the spacesuit. The back of the spacesuit, there's battery and lithium hydroxide CO2 scrubber. CO2 scrubber has to be replaced after every EVA. It's good for about 12 hours. And the batteries, normally if you're only going out once, you don't worry about recharging the batteries, but since we were doing successive everyday EVAs, we would have to take the batteries out every night, charge them, take the ones that had been charged, put them into the suits that are going to go out the next day, and just keeping track of which cartridges have been used and which batteries have been charged and how much. I mean, there's a tremendous amount of overhead effort just in managing all of this equipment, and we had practiced doing this a lot on the ground, as you can imagine, before we went up. Okay, so the morning of the EVA, you get up early, eat as big a breakfast as you can because you're not going to get much to eat for the next 8 hours. These are radiation monitors. For Hubble, we were actually up at about 600 kilometers, which is as high as the shuttle ever goes. So we got really the highest radiation dose that you can get on the shuttle on a normal mission. It was about between 1 and 2 rems, which is not, no big health problem, but typically the dose on a shuttle flight at a more typical 300 kilometers is more like tens or maybe a little over 100 millirems. So they did want us to take the radiation monitor. So now we're in the middeck, and when you see these pictures, you get a sense of when you're doing an EVA, the entire middeck is just full of stuff. I mean, there's so much equipment. You've got the pants units floating over there, and plus the 2 extra suits and all of the auxiliary equipment. You try to keep things organized. So then there's for thermal control. The original Apollo spacesuits were designed for daytime use on the moon when it's very hot, and in addition, people are walking, so they're putting a lot of metabolic heat into the suit. And so they were very concerned about being able to have sufficient cooling. So they developed a very, very efficient sublimator cooling unit. You have a little layer of ice that's continually fed from the bottom, and it sublimates, and that basically is how you get rid of your heat. And then you run your cooling water underneath that ice, and it cools off, and then it is run through they call it LCVG, liquid cooling and ventilation garment, which has lots of Tygon tubing that goes through it so that it carries the cold water next to your skin. And also, the oxygen that comes into the suit comes through the helmet over the back of your head, so it flows over your face. So you breathe the fresh oxygen, but you would like to get ventilation through the entire suit, so you don't build up lots of humidity in your arms and legs. So what you do is the return valve actually comes through these air ducts, and so the return is picked up at the bottom of your arms and at the bottom of your legs. So that ensures that the air does get circulated through your arms and legs. But when we started doing shuttle EVAs, metabolically you're not nearly as stressed. Plus, you spend almost half your time in the dark, and it gets really, really cold. And this has been a constant problem. We were very concerned about, and here's an interesting systems problem to show how everything relates to one another. When you open up the doors of the Hubble telescope, if direct sunlight comes in, it will cause an outgassing of the internal material, which could pollute the ultraviolet mirrors. The ultraviolet optics are very, very sensitive to organic contamination. So under no circumstances could we have sunlight penetrating the interior of the telescope. But we were going to be spending a lot of time with the doors open. So how do you ensure that you'll never get the sun coming in? Well, the Hubble telescope is sitting up here like this. So if that's the sun, just make sure that the belly of the orbiter is always pointed towards the sun. Then you never have to worry about sun coming into the telescope. But what you do have to worry about is that, during the day side of your orbit, if the sun is over here and the Earth is over here, during the day your payload bay is going to be pointed towards the Earth, and so you basically have a radiative heat exchange with something that's at about 20 degrees C. No big deal. You go around the other side now, at nighttime, you're pointed at deep space, and so you're radiating towards absolute zero, or 3 degrees Kelvin. And that is a concern. And you get very cold. They were predicting temperatures of as much as 150 below zero Celsius. We were very concerned, not only were our hands going to get cold, but some of our tools might not work. So we pushed very hard for a test in a thermal vacuum chamber where we can actually go through. Our tools are stored in a toolbox outside in the cargo bay, and we wanted to go through, going out, taking the tools out, and of course they're held in there because they have launch locks, and so there's little pit pins and latching mechanisms that you have to remove so that you can get the tools out. So I went in to do the first test, and what it is, it's a vacuum chamber, and the walls are painted black, and they can run liquid nitrogen through the vacuum chamber. And they could cool it down to the lowest temperatures that we were expecting to experience. I opened up the toolbox, and about 75% of the tools, the launch release mechanisms were just frozen shut. I couldn't get them out. So that started to get people's attention. So they sent the engineers in to redo some of the tolerance, and they played around with the lubrication a little bit. Then Story went in a week later to do his run, and he was able to get most of the tools out. I think he got all the tools out, actually, because I was only in for a few hours, because once we realized that it wasn't working, I came out. He was in there, and I remember he said at one point, he said, just holding on to these tools, my hands are really, really cold. And I don't know, about an hour or so later, someone asked him how his hands are, and he said, oh, they're fine, they've warmed up. Well, Story's from the South. Those of you with experience in winter know that if your hands are really cold, and after a while you don't feel them anymore, it doesn't necessarily mean that they've warmed up. When they took him out of the chamber, his hands were deep purplish black, and he had severe frostbite. to the point where, I mean, they sent him up to Alaska to some frostbite specialists, and they were, in the end, he was very fortunate. He got off with no major permanent damage, and he was able to fly. But, as you can imagine, that got serious management attention. So, gloves now have electrical heating units in them, but we didn't have that available. What we had to do was to change the attitude profile so that we were basically pointing towards the Earth. Now that's generally okay if you're pointing towards the Earth and the sun is coming from your belly, you're not going to hurt the shuttle. But a quarter way around the Earth, you do have the possibility now that the sun is going to hit the telescope. So what they had to do was to do 2 orbital maneuvers two attitude maneuvers every orbit in order to basically keep us in a more benign thermal attitude for the EVA, but to prevent the sun from shining on the telescope. And we didn't have the reaction control system propellant budget to support that. Remember, we were going into a high orbit, which meant we needed to use a lot of ohms fuel to get up there, and we needed a lot of propellant for the D-orbit, because the higher you are, the more you have to burn to get down. And so the propulsion and flight control community, together with the pilots, got together and developed a special way that we could do maneuvers using only half the number of jets that you normally use. And so this is an interconnection between the thermal environment of EVA and the reaction control propellant budget, which nobody, in the early days of flight planning would ever have believed that there's this sort of a connection. But it's just another good example of how these systems all play with one another, and you can't make changes in one without another. I'm going to finish this unit, and then we'll take a little break, and then I'll do the last part. So, okay, so process of getting in the suit. First you get in LTA, lower torso assembly, basically the pants, and of course this is one time when you can put your pants on both legs at a time. Okay, you can't do that too often. But again, look at the mid deck here. It's full. This, by the way, is the escape pole. We talked about this earlier. During launch and entry, it's actually bolted into position so that it'll take you out the door. But once you're in orbit, you just sort of float it up and out of the way, and it's just kind of Velcro to the ceiling, and of course it has no weight up there, so it's perfectly happy. Okay, so you get in the pants. Now the suit the upper torso of the suit is attached to the wall inside the airlock, so now you have to float into the airlock, and that's what you're looking at when you're getting into the suit. And there's a lot of connections you have to make. This is the water bag. This is the COM connection for your Snoopy cap. This is the water and air connection, which you have to hook into your LCVG. And these are the arms which you have to get into. And the problem in the design here is your shoulders are wider than your chest. So when you're actually inside the suit, you want the distance between these two arms to be conformal with your armpits, because if it's out here, that cuts way down on your mobility. But if it's too narrow, you can't get into it. Okay, so that's the basic design problem in this sort of a suit. Now the Russians have a rear entry suit which doesn't have that problem. So it's always a challenge, and you really have to push and struggle to get in, and eventually they wanted to design this suit so that one person could get in by themselves, but it can't be done. I mean, you can get in like this, but you just can't pull up the waist ring and attach it by yourself. Nobody's been able to do that. So it's a great feeling of accomplishment when you finally get inside. Then you put your helmet on. So now you're starting to see what we're dealing with, because we have to take all this stuff outside. in addition to the tools that are already outside. These are the plugs which we put the mini workstation. We haven't put it on quite yet, but it's just a whole bunch of equipment which you have to manage. And at this point, we're breathing pure. We purge the suit with an oxygen flow. Now remember, we're at an atmospheric pressure, or almost an atmospheric pressure, I'll get into that later, of pure oxygen. So that also puts very serious flammability constraints. Although when you go outside, you're only at 4 psi. When you're inside here, you're at the full cabin pressure. And actually, in order to do your leak check, you have to go to 4 psi above cabin pressure. So you're actually working at above 1 atmosphere of pressure of pure oxygen. So that's a very serious flammability design constraint. And we have to sit and breathe pure oxygen then for about 40 minutes to get the nitrogen out of our blood. And again, I'll be discussing this whole atmospheric and bends problem. But if you don't, when you drop down to 4 psi, the nitrogen in your blood bubbles out and you get the bends, just like a diver who comes up too fast from a dive. So just 1 or 2 pictures of what went on outside. There's Hubble. I was changing some fuels there. It was kind of neat working underneath the solar panel. Those were the old ones which we took off and replaced the next day. But you have to be really careful because you don't want to bang against it. And of course, you can't see above your head. So we always have other people looking at us. This is the kind of situation where if you had a little heads-up display where you could get this sort of a view to show what you're really doing, it would really improve your situational awareness. But at the moment, we don't have that. So it takes not just the people outside, but the people inside paying full attention, reading procedures. Historically, we carried all of our procedures on a cuff checklist, like so. But the procedures for Hubble and some of the other flights are so complex that you just can't do it. So nowadays, these are just emergency procedures. I'll pass this around. You can. I would like it back. Okay. Let's see. After putting in the new whiff pick, Ground had to do some tests on it. So I got Claude to fly me out over the arm, and we had one of the old lunar Hasselblad cameras, which they let us carry. Normally we just use Nikons on the shuttle, but we let us take a Hasselblad, and so that gives a view of what the payload bay looks like. EVA. There's Story over here working on one of the other things. The Earth is not flat. Don't worry about the picture. I went around it many times. And then, I mean, some parts of EVA, I really should share it because, it just gets really spectacular. This is about 50 feet. I don't know whether to say above or below or, whatever of the shuttle, but, you're just out there in the middle of nowhere. And at this point, I was the free floater. One of the people is always attached to the end of the arm, which is good when you have to move around big pieces of equipment because now you can react the forces with your feet. When you're a free floater, one arm always has, either you're in a foot restraint, which limits your mobility, or one hand has to actually be holding you so that you can react forces. What was really neat, of course, we are attached by a waist tether, which is then attached to a long reel of stainless steel. But you can set it so that the springiness is taken out, and so I could basically, and I did from time to time, just sort of let go, and it's a really neat feeling because once you convince yourself that you're not going to fall down. Which I'm enough of a physicist to understand the orbital mechanics, but nevertheless, the first time I let go, it was an interesting feeling. But the thing is, when you're holding on to something, whether by your feet or your hands, of course, the shuttle is so much more massive that you feel yourself physically related. You're controlled by the shuttle, and so the shuttle is your point of reference. Maybe the shuttle is in orbit, but you're attached to the shuttle. As soon as I let go, the physics totally changes, and it was really this transformation into being a human satellite. I mean, I really felt like I was a satellite now. I wasn't attached to the shuttle, and sometimes, you know, if I could turn around so that before I let go, so I didn't see the shuttle, it was really kind of neat, especially at night, you know, just sort of floating there and all the stars and everything. So, yeah.
They build in time for you to be able to kind of do that kind of thing.
They don't build in the time, but again, you know, we like in this case, 2 days before on Stories in my last EVA, we had not replaced. We had these are the magnetometers up at the top. The gross maneuvering of the shuttle of Hubble is done by reaction wheels, but the reaction wheels, when they get spinning too fast, you have to be able to desaturate them. So they have magnetic torquers, these long torque rods, which create a magnetic field. They interact with. There's no jets on Hubble because it would cause pollution of the optics. So you need magnetometers up at the top to sense the magnetic field in order to operate the torquers. The magnetometers were never designed to be replaced. They weren't supposed to fail. Well, both of them failed in the first couple of years. We couldn't take them off, so they designed 2 new magnetometers that we can actually insert and bolt on top of the old ones, and then we took the electrical and data connections and hooked them up. But I noticed on that day, because you know we were very concerned with quality control, making sure first of all that we didn't break anything that wasn't already broken, but also to look for any signs of damage, because you know this was a telescope which was supposed to be maintained. We saw a little bit of paint chipping off the outside of the old magnetometers. They were concerned that they might float around and get into the optics, so we went into the payload bay on the next day, the other EVA team, and they cut off some of this gold insulation material from one of the thermal enclosures that some of the equipment was in. And I'm not supposed to stand in front of I keep forgetting that. We made those covers, and then we had to go up and install them. But you know, actually, after we installed them, then the ground wanted photographic documentation. So we took pictures, and then the crew inside got their telephoto lenses, and they took a lot of pictures, and then they got the television camera on the end of the arm to take pictures. And so during all that time, you know, you do have a little bit of free time just to sort of enjoy the environment. It'd be a shame not to, because it's such a spectacular place. Yeah.
How do you work when there's no light, when you're in the dark?
These are. Let me turn the laser pointer on here. Oh no! What did I do? That's a good time for a break. Okay. Take a 2-minute break. Good grief. And then, of course, when the sun rises, you know it, so you can turn your lights off. Okay, I talked about the necessity of doing a nitrogen purge and pre-breathing oxygen to get the nitrogen out of your blood. This turns out to be an interesting systems problem, because it doesn't just affect the suit, it affects the spacecraft. Those of you who were here at the beginning saw I was blowing up a balloon, which unfortunately popped. It was only to make the point that you can look at a spacesuit, you know, the arms and legs, cylindrical. It's like one of those balloons, and you know when you try to bend the balloon, it doesn't like to stay bent because you're compressing the gas and you're doing elastic work on the material of the balloon. And it wants to snap back. And spacesuits basically work the same way. The old-fashioned pressure suits that test pilots used to wear, which were the genesis of the original Mercury suits, they basically stiffen you. And in fact, the launch entry suits that we use on the shuttle are not designed for joint mobility. They're just pressurized. And you know, when we do a pressure check before the mission, when we're getting suited up, and they blow it up, and you just go like that, and it's, you can move a little bit, and enough so that if you're sitting in your seat with a seat belt holding you in form so that your waist is bent. You can move your arms enough to get to the controls, but I certainly wouldn't want to try to go out and do any useful work in that. So it's really been an extraordinary design process that people have been able to develop spacesuits with articulating joints that allow us. I mean, it's certainly not like walking around and doing things in your just with your body, but it's amazing how flexible spacesuits are, and it's a continual challenge to develop, particularly for the gloves. And when we get back to the moon, to have legs that you can actually walk in, so that you don't have to hop around all the time. Although there are times when that's good too. But in any case, the stiffness of a suit, because it turns out that most of the stiffness comes from compressing the gas. So you want to try, first of all, to build articulated joints that don't change their volume. And actually, people have designed metallic suits that look like, Robbie the Robot, so that they truly are zero delta volume suits. Problem is they're very heavy, and there are other problems with metallic suits. I don't have time to go into that. Given that you're going to have some volume change, the amount of work that you do is thermodynamically pressure times volume. So you're going to have a delta V. You want to reduce the pressure. So the lower your suit pressure, the easier it is to bend. So basically, you don't want to fill your suit with any gas that you don't really need. We certainly don't need nitrogen to stay alive, not on a short-term basis. So we fill the suit with oxygen, and we run it at about 4.3 psi for the shuttle. This is just historically Mercury, Gemini, and Apollo. The suit pressure was a little bit lower. Doctors felt after doing calculations of the actual, what you're really interested is in the partial pressure of oxygen in your blood, and they wanted a little bit more margin, since the shuttle was supposed to be operational this and operational that. They wanted a little bit more margin, and so we bumped up the suit pressure a little bit. Mercury, Gemini, Apollo cabin was 100% oxygen at the same pressure, so that you didn't have to worry about pre-breathing. In Skylab, it was not pure oxygen, but it was a high enough oxygen that, again, they didn't have to worry about pre-breathe. It hasn't been until we went to the shuttle, which typically the shuttle is at 14.7 or 100 kilopascals, normal atmospheric pressure. And if we know we're going to be doing a lot of EVAs, and I'll talk about this later, what we do is we drop the overall cabin pressure, but we keep the partial pressure of oxygen the same, so you end up bumping up the oxygen concentration. We don't do that with the ISS. Decision was made by the life scientists that since they wanted to study biology on the space station and all of our database is at 1 atmosphere, that if they took the space station down to 10.2 psi, basically it would invalidate all of their life science research. So the station was only designed for 1 atmosphere. The operational people, when they started to talk about how much EVA was going to be involved in building and maintaining the space station, the astronauts said, "This is crazy." And you'll see the impact of this later. This is just looking in the future. These are decisions that are going to have to be made for future space systems, and they are looking at a lower working pressure, and you'll see why as I go through this presentation. I think I'm not going to go through those charts, but again, this is a system, so you're affecting a great many different things. Let's see, which is the laser here? Laser. There we go. Okay. So This is one of the interesting things here with EVA, just like in any ECLS system, is that the human body becomes one of your subsystems that you have to take care of. And in many cases, we don't have a whole lot of design flexibility with our bodies because they come pre-designed. Okay, so we have to deal with that. So we've got all of the physiology, the bends, materials. I talked about flammability in a pure oxygen environment. I talked about the constraints of microgravity and partial gravity physiology studies in the ISS. Of course, NASA has decided that we don't need to do that anymore. So, but that station was. And I guess our international partners are still going to want to do this. And in any case, the station is designed. The cooling, we talked about, I think, in the ECLS section lecture, the fact that if you drop your cabin pressure, now you've got to pump more air for all the air-cooled things. And if you really want to design for a variable cabin pressure, then you're going to have to spend that flows over into the cooling requirements, more water cooling. Different fan requirements and so on, and it goes on. If you're going to do multiple EVAs, the amount of what you're really interested when you're looking at efficiency is we call it EVA work efficiency index. It's the total amount of time involved in preparing for and carrying out an EVA. The ratio of that to the actual useful working time you get outside. And the more time you have to spend breathing pure oxygen to denitrogenate your blood, that's taking away from your overall work efficiency. When we do tests on the ground and we start out at normal sea level pressure, and we want to go down to 4.3 psi pure oxygen, we actually have to do a 4-hour nitrogen purge. So we have to just sit in the suit or stand in the suit for 4 hours. This is in the EVA test chambers before we actually can go down to pressure. If you want to get an 8-hour workday of EVA, that's just unacceptable. And that's why they made the decision to lower the shuttle's cabin pressure, and then you only have to do about a 40-minute EVA. And I have some of the specific numbers on that later. So, as I say, just the review here is that we do have this capability on the shuttle. We don't have it on the station. They have figured out a few ways to make the denitrogenation process a little bit more efficient in the station, but it's still a big overhead hit. And we're very concerned for the future because, EVA is not just an afterthought when you're going to be exploring on the moon or Mars. You're going there basically to do EVA, otherwise why bother? So we've got to deal with this. Okay, here's the basic physiology that we're dealing with. Oxygen percentage on the abscissa, total pressure on the ordinate, and all different units, millimeters of mercury, PSI, and I think I have now people use kilopascals, which I don't really relate to, but I know about 100 kilopascals is about 1 atmosphere, so luckily that makes it easy. So, normally we're at 1 atmosphere, 20% or 21% oxygen, we're up here, and this is the normal sea level equivalent. So, you start dropping the pressure, and you have to increase the percentage of oxygen, okay? There is a maximum level of breathing oxygen at pressure, oxygen toxicity, because oxygen is almost totally absorbed through your alveoli. And if you have, normally our alveoli stay inflated because we have 80% nitrogen, which is only very reluctantly absorbed. I mean, it does get through, that's how it gets into our blood and so on, but it's a much slower transport. But oxygen gets right through, and if you breathe pure oxygen for a long time, your alveoli, you can really hurt your lungs, and it can be lethal at a certain point. We actually don't have any good physiological data. I was down in Houston last week at a big EVA conference. That's why we didn't have class on Tuesday. And they were talking about, what about long-term planetary EVAs, even at 4 psi, pure oxygen? Is that going to be harmful to health? We honestly don't know, and that's an active area which needs research. On the other side, of course, you get into hypoxia, which you've all heard of. You get it when you go up on Mount Everest and so on. So you've got a boundary that you have to work in. Now, this is sort of where things have fallen. The blue line is the hypoxic boundary. Green line is normal oxygen. When we were using pure oxygen spacecraft environments, we were well above that, and you'd like to stay as close as possible. With shuttle EVA, we moved a little bit closer to hypoxic, but we're still in a physiologically perfectly reasonable environment. Decompression sickness, just a quick review. Any scuba divers here? Okay, so you're all familiar with this. There's various levels of decompression sickness, anywhere from just a mild tingling of the skin to joint pain to phase 3 DCS, where you get central nervous system impairment, which can actually cause death. So you don't want to mess around with it. People refer to this famous R value. You run into this all the time. What you're really interested is, what is the ratio between the actual partial pressure of nitrogen in your blood compared to your suit pressure. And this over here shows, this is that R value. If you're down at 1, the nitrogen isn't going to bubble out at all, so you have no incidence of bends. VGE, venous gas emboli. Okay, so, and then as the R value increases, the dotted line, gas emboli, that just means you have bubbles forming. DCS means actual symptoms of bends, and then grade 3 DCS, which is very serious indeed. The way they make these measurements, they have these large physiological studies where they actually get people to volunteer to go through these pump-down protocols, and then they actually put sensitive microphones and ultrasound things that can actually hear the bubbles as they move around your veins. I've never been able to figure out why anybody would volunteer for these experiments. I take my hat off to them. Because the only way you build up this data is that some people actually do get the bends from these experiments, and of course they have hyperbaric chambers, which as soon as there's any symptoms, they put them right into the chamber and pump them to pressure, and it goes away. And I don't think that they've lost any volunteers, but like I say, that's not something I'm going to volunteer for. Other factors, and this is something that becomes important. It turns out that the amount of time you spend at reduced pressure is important. Also, exercise. It turns out that the more you exercise, maybe it makes sense, you're moving your joints around, but the bubbles come out. So actually what they've started to do on the space station, since we can't go to a reduced cabin, that while they're breathing oxygen for the first hour or so, they do very exhaustive exercise, both upper and lower body, on an exercise bike with arm exercise as well. So try to drive away as much of the oxygen early on in the decompression, in the preparation as you can. Okay, so where does that put us? As I said, the more nitrogen you have in your blood to start out with, the longer a pre-breathe you're going to have to do before you can go out. So these are the normoxic and hypoxic lines, which I showed you before, and then these are the contours of the amount of time you have to pre-breathe. So, okay, remember I told you if you're at 1 atmosphere, 20% oxygen, your pre-breathe time is 240 minutes, 4 hours. This is to get yourself down to an R value of 1.65. So this is not 100% safe because, remember, at 1.65, which is where these data, there still is a, 25% incidence of DCS. Now, the interesting thing, these are the statistics that come from the laboratory trials. We've never had a reported case of bends during EVAs, and people aren't quite sure why. Some people suspect that maybe even if an astronaut is getting joint pain, they're not going to report it because you don't, maybe that would prevent you from doing another EVA. It also could be, there's enough other pains that you undergo in just using a spacesuit that maybe you don't even notice it. You feel a problem in your joints or your fingers and you say, oh, damn it, my gloves don't fit right, or, something like that. So, but it also, and I have another slide mentioning this later, there is some suspicion that weightlessness may have an impact, which means that the bends susceptibility on the moon or on Mars may actually be greater than it is in weightlessness. We just don't know. Okay, here's where we've gotten to on the shuttle EVA. Again, this is no pre-breathe. This is 1 hour pre-breathe. So we're at about 40 minutes on the shuttle, and that's where we are. Now, this is a design problem. How are we gonna design the CEV? How are we gonna design the equipment, the habitats that we're gonna use on the moon and Mars? So now we're talking about surface exploration, and as I said, there's a lot of uncertainty about the effect of gravity, but we suspect that it may be more bends inducing than weightlessness. And so what they're doing for safety and conservatism is, instead of using the R value of 1.65, which we use on the shuttle, they're taking it down to about 1.3, 1.4, okay? Now what does that do? Here's 1.4, 1.3. Where does that put the shuttle EVA? We now would have, to get down to that R value, we've got a 2 hour pre-breathe. To get down to 1.3, we've got a 2.5 hour pre-breathe. So now, and this is with the normal spacesuit at 4.3 psi. We're hitting an operational problem. You want to go out on your geology traverse on the moon, you got to depressurize, denitrogenate for 2.5 hours. I don't think so. But what are we going to do? Well, if you increase the suit pressure, now the R value at a given level of nitrogen, the R value goes down, and so at 6 psi, even for an R of 1.3, you're in the 0 pre-breathe range, which would be great. So people have suggested, well, maybe we should build a variable pressure suit so that you could go out at 6 psi, sort of get things set up, and then all that time counts towards your denitrogenation. So maybe then after 2 hours into your EVA, now you can drop your pressure, and now if you have any things where you need more dexterity, you'll be okay. But the pressure control system in a spacesuit is a very complex undertaking. The Russians do have a dual pressure suit. They never use the lower pressure, to my knowledge. And it's a big hit to try to design this into the suit. And of course, to design a suit to operate at a higher pressure, the Russians work at about 5 psi, but it means your suit is less flexible, heavier, and it's just going the opposite direction from the desire to accomplish useful work, which is why you're putting on the spacesuit in the first place. So this is what we're working against. Again, we've got a systems problem. It's not just the pressure, it's the oxygen. In Skylab, in Apollo, because you were working in a pure oxygen environment, now, of course, now we're talking about what is the pressure going to be in a cabin. right? So you want to keep the cabin at a higher oxygen environment. Your material selection is highly limited. So as it says, they tended to use a lot of metallic materials. Well, what do we know about metals, particularly aluminum? Well, first of all, aluminum will burn, but at 100% oxygen. But okay, your cabin, even if it's not 100% oxygen, you're going to have a lot of metallic material. Well, metal is, when you're dealing with radiation, you hit metal, aluminum or higher, even higher Z, higher atomic number metals with primary cosmic rays, and you get spallation, produce a lot of secondary particles, and you end up with actually more radiation than you would have gotten if you had just gotten hit by the incident cosmic ray. What you really prefer is to have a low atomic number. Hydrogen is best, water, hydrogen and oxygen and so forth. So, if you're forced to increase the metallic content of your spacecraft because of the oxygen flammability problems, now you're going in the wrong direction for radiation protection, which becomes an issue when you're dealing with long duration stays on the moon, interplanetary transport, and so on. So it's all interrelated. You can't change one thing without changing the other. Flammability, well, we've been talking about that. I won't stay on that. But again, it is very dependent on oxygen. Oxygen restricts the use of nonmetallic materials, but nonmetallic materials are what we would like to use from a radiation point of view. You'd like to have a lot of hydrocarbons, polyethylene, plastic in your spacecraft, because they absorb cosmic rays. Doesn't work. But in any case, it's pretty well agreed that we never want to go above 30% oxygen. It just becomes too restrictive on the types of materials we can use. So that's going to be a design constraint. Remember, we're aiming towards a systems level design of our long duration space habitats which are EVA compatible. So 30% oxygen. All right, so now we're back to this. Now we can draw a red line, and we've got to stay on the left of that line. We've got to stay above the blue hypoxic line. Now, also, remember that we've got these pre-breathe lines. So let's say that we're going to limit pre-breathe to no more than 1 hour. Well, we're cutting down on our design space here. We've got the oxygen flammability, which is cutting off to the right. We've got the hypoxic limit, which is cutting off in this direction, and we've got the pre-breathe limit, which is cutting off there. And we're kind of in I won't call it a box. It's a rather small triangle. Now, if we go to a 6 psi spacesuit, as I said, we open up the design space a lot, but at a price of flexibility, maneuverability, and the ability to do the things that we want to do in the first place. So, where are we going to go with this? As I say, it's an active area of research. I can't tell you what the answer is going to be, but it looks like they're going to probably be going for 8 to 9 psi with a oxygen concentration approaching 30%, and that the CEV, from what I've been told, is most likely going to be designed with a variable pressure capability, because it also has to be able to dock with the space station, which means it has to be able to take 1 atmosphere. And also, because the CEV by itself is not going to have an airlock, you're going to have to be able, if you'd have to do an emergency EVA out of the CEV for whatever reason, you're going to have to depressurize like we did back in the Gemini and Mercury, well, the Gemini days, or Apollo. And of course, that is going to affect the design of all the other systems on the CEV, because they'll have to be able to operate from a vacuum all the way up to a one atmosphere. So just in the end, I hope what you've gotten out of this is, again, we're trying to look at things from a systems engineering point of view, and this is one big system where EVA cannot be considered just on its own, because it affects, I gave an example of how it affects the RCS system with Hubble. Here it affects the environmental control, life support, flammability, radiation protection. It's all linked together. So yeah, this was the recommendation that we came out with, was slightly below 9 psi at pushing 30%. But as I said, there's a lot of research that has to be done to understand the way bends behave at partial gravity. How we're going to do that, I have no idea. But as I said, for the International Space Station, we have to be able to go up to regular atmosphere. And I think, yes, that's what this was. We were making this presentation as part of the study we were doing last year on CEV, but it was so relevant to what we did here that I didn't see any point in modifying it for this class. But we had to make these decisions on the shuttle based on similar calculations, looking at the design space. The difference was with the shuttle, we were using an R value of 1.6, 1.7, and so we were able to get down to a 40-minute pre-breathe. What we do with the shuttle is about the day before you're going to do your first EVA, you actually drop the cabin pressure. There is no, and I think when we had the lecture on environmental control, you remember there's a cabin pressure controller at 14.7 and a pressure controller at 8 psi. But when they designed the shuttle, nobody was thinking about EVA or about this pre-breathe time, and so there is no 10.2 controller, so we have to do that manually. You drop it and then you add a little bit of nitrogen or a little bit of oxygen depending on what the instrumentation tells you need, and then there's a periodic maintenance which you have to perform in order to keep the proper gas concentrations. And then when it comes time, and then we leave it down there for the duration of all the EVAs, and then when the last EVA is finished, then you turn the 14.7 controller back on. Now, of course, since you have the proper oxygen partial pressure, most of the gas that comes into the cabin is nitrogen. And it actually, I think we may have mentioned this before, it comes in the bathroom. And so for the time when you're repressurizing the cabin, bathroom is off limits. And I think that's basically it. And the timing has been pretty good. Questions, comments? Yeah.
Is anybody looking at using a fully 1-atmosphere spacesuit? I know it would be basically
actually, it turns out there's a principle called Haldane's principle that says that if you don't change your and let me actually in the other presentation I had where is it now? Yeah, let me get this up because I have some pictures of what we were doing. If you change by less than a factor of 2, you don't get the bends. This is an empirical finding. And so the idea was if you could have a suit that worked at about 8 psi, you would have a 0 pre-breathe suit. And I participated in a bunch of tests. And let me, there's some other robotic things. Yeah. This was the hard suit designed by Ames. Because it's a constant volume suit, it's not sensitive to the pressure the way that a soft suit is. And we did a lot of tests actually. We always came unstuck on the gloves. Nobody's been able to design an 8 psi glove that really gives you sufficient mobility. And I mean, it's a dream. People would love to be able to do it. If we could figure it out, that would solve all these problems. Although, if you're going to Mars, maybe you don't want full pressure because if you have 1 atmosphere compared to 8 or 9 psi, your structure has to be that much thicker and heavier. They went through some of those calculations. This is now on the other hand with the space station, and they figured that for all the meteorite shielding and everything they had to put on the outside of the space station, that actually the change in thickness that would be involved in changing the pressure from 1 atmosphere to another really wouldn't make that much of a difference. So, all of these things, again, they're interrelated. But it's a good point. Yeah, I mean, that's why I showed those designs for 6 psi, because people are still thinking, suppose we could design a spacesuit to work at a higher pressure, but right now we don't know how to do that. I hope everybody has a very happy Thanksgiving. We will see you a week from today. If there's any questions, again, about either your oral presentations or the written presentations, I'll be here today, and then I'm gone for the rest of the week. But I will be looking at emails, so you can send me emails and we can discuss things. Okay.